All right, so next and final thing is we're going to talk about torque on a current loop. So still talking about this magnetic force, but if we have a current running in a loop and we have a magnetic field, a uniform magnetic field that loop is sitting in, we'll describe how a torque is experienced by that loop. So that loop will want to rotate about some rotational axis. So let's look at that. So if we have, give me some room here. If we have, so let me do this. So 4.5 force and torque on a current loop. And this is going to be the basis for many, electromagnetic kind of devices, and an electric motor is torque acting on a current carrying loop. So if we have a loop of current, I'm going to use just a white thing here. So if we have a loop and it's at some angle like this, such that we have a z-axis that is straight up, we have an x-axis that is here, and we have a y-axis that's here. Oops. Right? So it's at some angle relative to it. What else do I need to describe? Then what is that angle? Let's see. So that angle we can say is given by phi, right? So this angle here, phi, oops, that's not phi, phi, I think that's better. Wow. Boom. All right. If we have some current going around this loop, it's going this way, here, it's going this way, here, right? It's going around the loop like this. And we have some magnetic field pointing in the z direction, right? Some magnetic field in this direction everywhere along the thing. So I'm going to do it here, right in the center of the thing, right? And here, right? Some B field in the z direction. Then what I want to do is talk about the force that is experienced by the different segments of this loop, given that there's a current in some orientation in a B field, right? Moving charge, current, in a magnetic field, it's going to experience some force if the orientation is right. So the force, which I used as yellow. So using our right-hand rule, let's talk about, let's do, this is segment 1, this is segment 2, this is segment 3, this is segment 4 over here, the 4 sides of this loop. So for segment 1, we have current. We put our index finger in the direction of current along the negative y direction. We have our B field in the z direction, and so the resulting force would be in the x direction, right? So the resulting force would be in the x direction. All right, so now segment 2, we have our current in this kind of diagonal direction down in the negative z and negative x direction. And we have our B field being upwards. And so we have some force that isn't, it's not the current and the B field are not orthogonal, which just means that there is going to be some angle between them that's not 90 degrees. It's going to be equal to phi, right? So the force for segment 2 is equal to I L cross B, which is equal to I L B sine of phi, and sine of phi is not going to be 1, but it'll be something. And yeah, and so we have some force still in the direction of our thumb. If we put our right hand up, that is outward in the negative y direction. And it's not going to be as strong as F1 because things aren't lined up as ideally, right? We have the sine phi that diminishes it from just being straight ILB, right? Whereas this is IL1B and IL2B. Even if the lengths are the same and it's a square, it's going to be less, but it's still in that direction, that outward direction. All right, so now let's look at segment 3. So for segment 3, put your index finger in the direction of current. You might have to rotate your hand quite a bit. You put your middle finger in the direction of the B field, and your force vector is given in the direction of the negative x direction. So force on the 3, negative x direction. And that is going to be, that would be equal to, if we're writing it out, IL3B, right? Okay. And then the last one, you can convince yourself, just like segment 2, that the force is outward on segment 4. So, and it's going to be equal in magnitude to the force on segment 2, because it's also, right, so F4 is going to be L4B sine phi. Well, if the lengths are the same, L2 is the same as L4, magnetic field hasn't changed, right? It's the same moment. Current hasn't changed. It's the same all around the loop. It's all in series. It's no way of thinking of it. And phi is the same. Then F2 is equal to F4. It's just pointing in the opposite direction. So there's no net force in the y direction, but there is a net force in the and then there's no net force in the x direction either, but there is a net torque because we have, if this is the center, we have this being our r vector and an f vector, right? And this is an r vector, right? So we can say this is r1 and this is r3. So, right, torque from the force 1 acting on this loop is given by r1 cross f1, right? And so there's some angle between them that isn't 90, and so there's some torque there, and then the torque from the third force is r3 cross f3, right? Rf sine of, we'll say theta, and this is theta. This is going to be the same theta. R3 F3 sine theta. We can give it a designation, theta 1 and theta 3, but they're the same. Okay, so there's two torques acting on this thing, right? And they're acting together. They're not canceling each other out. They're making this thing spin, making this thing want to do this about its rotation axis through the center. So there is some net torque on a loop. right? There's some net torque on this loop. And if we use a vector to describe the area of the loop, similar to how we did with, well, maybe you didn't see it with torque, but if we use a vector, I'm going to do purple here, which is different than pink, to describe area times current, we'll give it a mu, right? So this is normal to the surface of this area that we would be considering. It's normal to that area, and it's pointing in a certain direction because of the current. So the current is going around the loop like this, right? And so if you curl your fingers, this is another right-hand rule, it's the same thing, it's just the curly one kind of makes sense for loopy things, and the 3 orthogonal axis pointy one makes sense for other things, same right-hand rule. If you curl your hand around, your fingers around in the direction of the current is traveling around this loop, then your thumb is giving a thumbs up in the direction of this mu vector. And so this, this torque, net torque, is given by IBA sine of phi, which we can identify mu as I times A. Mu is I times A, and it's a vector, and A is a vector, so we can say IA. And so then, therefore, we can write torque as being equal to mu B sine phi. And of course, we know that to be just another way of writing a cross product, so we can write torque in its most compact and vector form as being a cross product of mu and B. And so what exactly is this mu vector called other than mu? It's called the magnetic dipole moment. So mu, close, magnetic dipole moment. And there you go, magnetic dipole moment of the loop. Magnetic dipole moments are all you really need in order to have an understanding of how magnets work. So I want you to read about this in your textbook, but it has to do with electrons that are moving around in little electron loops, right? And so just like current around this loop, and we used our right hand to determine this mu vector, in this case, you would have, let me draw this another way actually then. You would have a magnetic dipole moment from just one electron like that, in that direction. And that's just for one electron, right? And so therefore, if you have a bunch of these together, right, you have a bunch of electrons and a bunch of these atomic moments here, magnetic moments, and you can line them all up, then you get one ginormous magnetic dipole moment with all of them in a macro scale material like a bar magnet. All right, so the last thing that I want to talk about is a DC motor, electric motor. I'm going to do it in a new video.